I really enjoy this seminar. I want to continue it even after Corona, because that's only an opportunity to meet so many people. Very good. So we are now live on YouTube.
Hello, I said hello, Dima.
Hello.
Good to see you.
Yeah, good to see you too. Thanks for coming.
Good. Yeah, no, of course. Yeah, I think you are arranging such beautiful lectures. I cannot miss them.
Thank you very much.
Yeah, no, very, very good. Excellent.
Okay, are we ready?
Hi, Harish.
Hi, I think we can start. So it's a pleasure to introduce Wen-Wei Li from Peking University, who will tell us about the distinction of Harish-Chandra modules and its Ext-analogues.
Okay, so thank you very much for the presentation. So I'm really glad to be a speaker in this seminar series. Okay, so today my topic is about the distinction of Harish-Chandra modules and some Ext-analogues. So, okay, so I'm sorry, this is just a work in progress. So I don't have any slides for this talk, and instead I use some funny note-taking software program to do the zooming out. So, okay, so let me go straight into this topic. So, okay, so of course, the first part is introduction. And please feel free to interrupt me if there's some technical problems. So, okay, so the basic setting is as follows. So we start with a group G, which is a group of F points of some connected reductive group. As usual, so G underline is a connected reductive group over a local field. So just a local field. I will specialize to the Archimedean case later on. And I consider subgroup, a closed subgroup, of course. So, okay. So the basic problem of so-called distinction of representations is to study the Hom space on H pi to say C, or maybe there are some more general frameworks. Okay, so let me write it here. So even more generally, you can plug in some character of H here. And here pi is an admissible representation of G. The goal is to study this space of invariant linear functionals. And here, let me use some other color. So here, this is for F non-Archimedean. And there are even some so-called Ext-analogues. Ext-I, H, pi C, or maybe a more manageable quantity is the alternating sum of the dimension of these Ext groups. Let's call this EP, Euler-Poincaré characteristic of pi C. And some conjectures has been proposed, say by Dipendra Prasad in a paper called Ext-analogues of branching laws in a much broader framework, but for non-Archimedean fields only. So today, my topic is about Archimedean case. So let me now take F to be Archimedean. Maybe let's take F to be R. So how to formulate the analogous question? So you can either consider something like this: pi infinity C, where pi infinity is a so-called Katsuman-Wallach representation of G. And here the harm is the continuous harm. Over H. Let's call this the candidate 1. And the candidate 2 is of a more algebraic nature. So here we consider Hong H. When I write H, it is something like Gothic H, but I don't know how to write it. So here we consider something like this. Pi C here, pi is the Harish-Chandra module. So in this talk, this means a GK module. That is ZG finite. Here, ZG means the center of the enveloping algebra, of course. And the harm is just the usual algebraic harm. And let's say H is the algebra of H.
Do you also assume pi to be finitely generated?
Yes. Yeah, you are right. Yes.
Thanks.
Thank you. Over UG, so UG means the universal enveloping algebra. So, okay, so of course the second one is more algebraic. In particular, here I assume everything to be over F. So, but once you formulate things in this language, you can work with say over the complexifications. Maybe I should work with the complexifications in the beginning. Sorry, my notation is just somehow chaotic. Plus the same conditions. So of course here K is some makes more complex, defined by Gaussian evolution. So since this is an algebraic definition, so in the second case, it is clear about the Ext-analogues is also easier to define. So you can also consider Ext-analogues. Ext-IH that is computed in the category of H modules by in a purely algebraic way. Also EP, pi C, and so on. Assuming that these Ext groups are finite dimensional. Of course, later on we will assume H to be spherical, so this is a no result. Personally, I haven't seen any formulation of the Ext-analogues for real groups in the literature. So I don't know if this is the only candidate of Ext-analogues of distinction of Harish-Chandra modules, but I think this seems to be a reasonable candidate to study. So the topic today is try to propose some way to study these Ext groups and the Euler-Poincaré characteristics for spherical H. So, okay, so I need another page. So wait a minute. Okay, let's go to the second page. So by the way, the two candidates 1 and 2 are, of course, related in a well-known way. So say if pi is, you start with the Kasselman-Wallach representation and you take the k-finite part. That will give you a Harish-Chandra module, and then the algebraic version is larger than the analytic version. And the so-called automatic continuity conjecture says it should be a quality. Today I will concentrate on the algebraic case, so I won't make use of the automatic continuity. Anyway. Let me draw something here. Okay. Great. So here are some. Wait a minute. Yeah, in order to formulate these conjectures, I mean, for example, to define Euler-Poincaré characteristic, you need some assumption. For example, xi is 0 for I large, and all these groups are finite dimensional over C. So I will mention these properties later on. So okay, so now let me state our basic setup. So now I start with G, K here. Let's view these groups over C. This is the usual convention in study of Harish-Chandra modules, I guess. And I consider the homogeneous space G over H. So let's assume this to be a spherical. That means there exists an open Borel orbit. So let me remark this, that this is usually called absolutely spherical because now I'm working over C. Of course, this is a very strong assumption, but I don't know how to do without this. Yeah, over C here. Moreover, I make another assumption. I need X to be affine. I don't know if this is really necessary. Maybe something will work for quasi-affine X. I'm not sure. So let me fix the base point. So this is just the identity coset. So that it's just identity. So the stabilizer is just H. Okay, so some more notations. So we have some familiar rings, OX, OX analytic, and OX head. You know what these are. This is, the first one is just the usual local ring. You know from algebraic geometry. And this is the ring of germs of analytic functions at X. And this, the final one is just the formal version, formal germs, formal functions at X. So the tool I will use today is D modules. So let's call DX the ring of the algebra of D modules. maybe just the ring of algebraic differential operators. On X, and again, we have the analytic version. So now we have a G action over X. So we get a natural map from UG, enveloping algebra, into DX. That's a map of algebras. What can we do now? So we want to study the Hom space of pi. Pi is now a GK module over H. So let's write this. Okay, so let me do this slowly. So the first thing is to observe. Okay, well, first, let's take Hom G. First step is to observe that this equals Hom G of pi into OX hat. We call it GX on a local ring in the usual way, say, by taking derivatives. So it's also X on the formal completion, and here you are just taking the usual Hom. So this one is, I think this is more or less standard result. I don't have a good reference for this. Okay. And the second isomorphism is even more standard. It's just some basic resulting algebra. So you make let's write UG here. So you make a change of rings from UG to DX. So get something like this, DX. And here you have DX tensor UG. Here this is a homomorphism of algebras. Pi. Here you get OX. Yes. And this is maybe not so cute for some people. So maybe you can localize. I mean, you take just the stock at X of the ring of, or the sheaf of the D modules on X. And you may go one step further by passing to completion. I mean, to analytifications, and you will get some Hom space like this. So far, it seems like I'm making our original question more and more complicated. So what is good about this? Let me give a name to this tensor product inside. So this is nowadays called the localization of the G module pi. Here I just care about its G module structure. On the G space, I mean variety with GX on X. So this is a fairly standard procedure. Once you have a G module and you have G, capital G acting on some variety, you can get a D module on X. Okay. So I just found that there's a talk by Ganev in the same seminar series. It's also about the localization functor. So what's good about this? The fact I will use is let the guy I mean localization here. This D module is some very cute D module called the regular holonomic D module. Let me highlight this fact. Oh, not good enough. Okay. So you might ask, what does a regular holonomic mean? So I will give a characterizations right now. So, okay, next page. Wait.
Wen-Wei, can I ask you whether this is related to being spherical variety?
Yes. Yes, it's regular only for spherical. I mean, absolutely spherical varieties. So that's proven in one of my preprints. So,
in one of your preprints?
I mean, yeah, I have some preprint called the regularity of some D modules. That's the main theorem there. So what does regularity mean? Maybe this is not really a characterization, but oh, sorry. Maybe this is I'm cheating somehow here because I'm passing to the analytic point. So I'm talking about regularity of analytic D modules. But once you have an algebraic D module that's regular, then its analytification is also regular. So, okay, so let N be such a D module, analytic D module. Then N is a regular holonomic if and only if for all x. Here, capital X is just some any smooth variety over C, even any complex manifold. If and only if for any x, if you take the same construction as above, then this actually equals this one. So to understand this equality, let's give some remarks. So this is just a space of formal solutions of the differential equations specified by N, and somehow sloppy here. Anyway, you can think about D modules as an algebraic way to organize a system of algebraic differential equations, linear differential equation, I mean. So left-hand side is a space of solutions, formal solutions at some point. And here is the same space, but analytic, gems of analytic solutions. So this means if you have a differential system of differential equation that is, then I mean a system of differential equations is regular holonomic if and only if every formal solution converge locally everywhere. This is a criterion of regularity. So now we can go further. So let's go back to the original isomorphisms. So once you know about the regularity, then you get something like this, home, H pi c. It is isomorphic to a home of the localization. Complicated. Okay, let's put an N here. That's not necessary. Yeah. And the good thing about this is this guy is finite dimensional. So this is the theorem due to Kashiwara, but I think it's also found independently by some other people. So in particular, you know the Hahn space on the left is finite dimensional, but of course this is a good result, but there exists simpler proofs that works in even greater generality. But what I want to say today is we can do get even a stronger result using a tool using the language of D modules. Well, let me go back to the fact I just mentioned. For regularity. So the key observation is that if you have a variety X with G action, as before, and you have N that is finitely generated DX module. That is locally GG finite. This means every element is contained in a finite dimensional GG stable subspace. And it is also locally, this guy is also equipped with a K-equivariant structure. As D modules. So there's a notion of equivariance of D modules on the group action. So once you have these results, once you have these assumptions, then you can get the regularity. This is proven in my preprint about the regularity. So in fact, this is not a very original theorem. So this is based on techniques from Ginsburg. A paper in 1989. So if you apply this to dx tensor pi over UG, you will get the regularity. So of course, you have to check the assumptions. So finite generation over dx is actually obvious because pi is finitely generated over G. So yeah, the first assumption is easy. And the final assumption, K equivariance, is also easy because it comes from the K part of the GK module structure. Because pi is a GK module. And the remaining one, GG finiteness, locally GG finiteness. is more tricky somehow. It suffices that it is generated by a GG stable finite dimensional space. Finite dimensional space. Once you assume this implication, then this is also also easy somehow. Generated over dx. So if you have seen my preprint cited there, then this is stated just as a remark. But yesterday I found this to be somewhat non-trivial. So maybe that's trivial for you. But okay, I will return to this point later on. So this is the main tool. I mean, maybe only tool I know about to deduce regularity in this setting for the study of Harish-Chandra modules. So okay. So I wrote something about a regular holonomic. So it's something called holonomicity beyond the. It's another notion beyond the regularity. So let me make some remark about this. Oh, this. Remark is if you only care about the holonomicity, then it is proven earlier by Eisenberg, Gurevich, and Minchenko. And I stated this only for relative characters, but the argument actually holds in our case. I mean, for the localization of a Harish-Chandra module. Okay, so I said this might be of some use for higher Ext groups. So let me get into the higher Ext. Okay. So the first thing is, okay, let's call this the easy part. Easy part is for any G module pi, even H module. We can consider xi h of pi with 0, even with any other thing you want. That is 0 if I is greater, if I is either negative or greater than dimension of h. So the reason is we can take a standard resolution, also known as the bar resolution of pi. And the number of turns is just dimension h. Here, pi is just as a h module. So the next thing to verify if you want to study Euler-Poincaré characteristic is about the finiteness of their dimensions. So the next hard part is to try to get some description of these Ext groups we want to study. So, okay, so let's do some undergraduate linear algebra. I mean undergraduate homological algebra. So how to compute the xi of pi? So the usual way is to take a projective resolution. First, let's do that in a category of G modules. Call this pi into a P naught, P1, and so on. They are only other terms. Then those PI are also projective as H modules. This is easy because PI is a direct summand of some free G module. So when you regard such a free G module as a HG module, it's also free. This is some argument I learned in the paper of Heisenberg Ravage. So maybe there's some categorical way to prove it. Just use a PBW theorem to show that UG is free over UH. Yeah, so this X group is the HI of the Hom complex. I should write a lower HI. I'm making some stupid mistakes here. So I should write a lower. I should use a lower subscript. Okay, so now maybe you know what I'm trying to do now. So let's iterate the earlier argument. So here I have these Homs, and I write it as a Hom of D modules. Put all the subscripts here. So here you have the localization now applied to P. And here you have the formal germ at X. So note that by some categorical reasons, this is also projective as dx module. I mean, before taking an identification and taking a stock, it's already a projective. So yeah, so this it's actually as a complex. This represents the derived tensor, or maybe a derived localization. And because you can take a finite resolution of this type, this is actually a bounded object. So here assumption. I want to go further. So assumption is, let's assume that the derived localization here, it is actually of a regular holonomic cohomologies. This means cohomologies are regular holonomic, or homologies are regular holonomic. If you take the homology of degree 0, then this just reduced to the theorem I cited before. But for higher cohomologies, this is not so clear to me. So let's just take this for granted. Okay, so let's take this assumption and go further. And then we take the original complex here. It represents home. The XX, you can also put an identification here if you like. You can replace formal germs by analytic germs. And I'm also cheating somehow here. So here I'm using some home version. For the regularity criterion I mentioned earlier for a single demargin. Here there is a derived version. This is also a known result. Right-hand side seems to suggest something. So, in particular, now you know that yeah, now you know the Ext group is just the Xi of this stuff. And yeah, and then this is finite dimensional for OI. And this is also a result of Kasiwara. And again, this is more or less a known result. So for X in a good position, relative to the maximal complex K, this is known. I saw this result in a paper by Eisenberg, Gurevich, and Klotz and Liu. But here, in this result, I don't need any assumption on relative position here. So note that this guy, home, before taking the stock at X, I just take the global version here. So in Kasiwara's works, this is denoted as SOL, means a solution complex, because it's in degree 0 cohomology, it gives you the solutions, analytic solutions of differential system. There's no. Sorry. No, it's a global thing. So if you take the start here, that's the one I wrote above. And if you take the Euler-Poincaré characteristic of this guy, you will give something like this. The dimension of the solution complex of this stuff. And you count the dimension of this stock at X. This is a C vector space, and Kashiwara's theorem tells you that it is finite dimensional. So what's good about this formula? Good thing is you can connect it with another theorem of Kashiwara. So this is not so convenient to use. This is called the local index theorem of Kashiwara. It expresses the Euler-Poincaré characteristic of, let's call this EP of solution complex. Of some holonomic, in particular regular holonomic, is okay. X. So there is some, sorry, I haven't prepared for this part. It is something, but it involves the characteristic cycle of N. This even makes sense if N is a regular holonomic complex, not just a single module. And also some geometric input, topological input, in fact, something called Euler obstructions. Of this characteristic cycle. I must say, I don't know. Even if it's true, I don't know how to compute it. At least it connects Euler-Poincaré number to something else. It's of a geometric nature. I hope this makes some sense for you. You can find all these Kashiwara's results in a book of D modules by Hota, Tanisaki, and Takeuchi. Standard reference. So far so good, but all this is based on assumption. That's what we call an assumption. The assumption is that the derived localization of Harish-Chandra module on X must be a regular holonomic complex, right? Something like this. And so far, I only said the degree 0 part is known, but how about the higher degrees? It's what I am trying to explain. Yeah, another page. Okay. This is the final part of my talk. Okay, so again, I want to apply the result in my preprint about regularity. So I have to check many assumptions about the cohomologies. Let's try to make this load. Wait. So okay, so it's something about this guy. About the cohomologies of this guy. So okay, so I want to apply the main theorem. In my preprint, let me go back a little bit for this result. So yeah, you see here. So here I said if I have a finitely generated dx module that's locally GG finite and it is K equivariant, then you can say it is regular holonomic. Trying to verify this condition. So first one, the easiest one is about finite generation of cohomologies. So this is the easiest part because pi is finitely generated over UG, and UG, UH, all these enveloping algebras are known to be Noetherian on the left and on the right. So you can take a freer resolution of pi free and finite. This means each term in this resolution are free of finite rank. In this way, everything you get is finitely generated, and dx is also Noetherian. Just reduce everything to Noetherian property, and to ensure that you will get, finally you will get finitely generated cohomologies in the resulting conference. So the second thing is you want to say, you want cohomologies which are D modules, dx modules to be locally ZG finite. Okay, let me try to explain this later on if I have time. The third part is, I mean, this is the most non-trivial part. It's about K equivariance of the cohomologies. So the problem is when you want to compute the cohomologies of this tensor product, we take resolutions as G modules. For example, the standard resolution of G modules. But in this way, okay, you get projective things even after localization. But the point is, you will lose K. So there's no K appearing in the final formula. So how can you get K equivariant things in this way? But if we take a solution of GK modules, okay, there is a well-known theory of homological algebra of GK modules. For example, you can see the textbook of Knapp and Vaughan about this. Then there's an opposite problem because projective GK modules are rarely or maybe never, I'm not sure, just rarely projective over G. over UG. So you cannot compute the X groups and so on if you take resolution of GK modules. So this troubled me for quite a long time. Okay, so I think there is a way to treat this difficulty. So idea workaround for this. I will try to end my talk in 10 or 15 minutes, okay? So there's something called H-complex or H-construction or H-derived category. So there are some, maybe there are 5 or 4 papers on this topic. I guess you will like paper by Bernstein and Lotz, 1995. So the idea is instead of considering complex of GK modules, consider complexes of weak GK modules. Weak means you do not impose any compatibility between K action and the G action on a module. But you need some extra data plus the homotopy, which is G linear between the K action, small K actions, obtained in 2 ways. The first one is from the capital K action, taking derivatives, and the second one is from the G action. So the morality is you consider complex of weak GK modules, so there's no compatibility, but you impose a compatibility up to a specified homotopy. And that's the basic idea. So I don't have time to write down an explicit definition. You can find it in the reference. In this way, you can get a triangulated category just as the usual derived category in this way. So it behaves well, just as a usual theory of GK modules with respect to maybe say direct sum of course, and also if you have tensor product of 2 G complexes, you can get GK actions on the tensor product, and also the homotopy also extend to the tensor product. So there are some standard operations. So the key example here is about the bar resolution. I mentioned the bar resolution, so here let's write down the explicit description here. So the bar resolution is a resolution look like this, minus here because it's homology. So it's a complex of G modules, G acting only on UG. K action is the diagonal K action. it's a resolution of the trivial G module K, G module C. In fact, the projective resolution is actually free. The point is, can specify a homotopy, a family of homotopy, to make it into an H complex as above. So when you pass to cohomologies, you still get something like K equivariance. So ditto if you take if you start with pi and you take ng times c pi, this is a projective resolution of G modules. And this is still, it's a tensor product to a H complex. So this is still naturally a H complex. And you get similar structures, H structures. Remember that H means homotopy. So this means you can specify homotopies everywhere. Represented by this guy. And in this way, you will get, maybe I have to check the details, but let's say this is just expectation. You will get a K equivariant structures on the cohomologies of homologies of this guy. Yes. This is a key example, the only one we actually need. Yeah, so to end my talk, I don't have that much time, but the last step is about the local GG finiteness. The basic idea is, this is much simpler. Idea is try to compute these homologies using a resolution. We try to show that it is generated by a finite dimensional subspace. It's stable on the ZG. Somehow this can be done. Yeah. I'm sorry, I don't have that much time, so let's omit the details. So yeah, so let me before end try to summarize. So what I'm trying to explain today is if you believe in this assumption, the red assumption here, something about the regularity of D modules, complex of D modules, then you can get the finiteness of various X groups in a distinction problem of Harish-Chandra modules. And you can even have a topological formula for the Euler-Poincaré characteristic in terms of something that's really hard to compute. For example, we don't know how to compute the characteristic cycle of n. I think you cannot solve this using abstract tools. You really have to do some computation. For example, when you start with pi, you have to realize pi concretely, for example, by cohomological induction, for example. And then try to say something about the characteristic cycle of its localization on X. And here, H construction, I think will still be some help here. If you want to interpret cohomological induction in this framework, but this is just some daydreams. I haven't made any progress about this. Yeah, so I have to stop here. Thank you.
Thank you very much.
So,
questions, please.
Can I ask a question?
oh yeah, please.
Is it possible now to make some computations of the X groups and Euler-Poincaré in some simple examples, let's say from GL2 to GL1 or GL3 to GL2?
Not yet. No, so far I don't have any idea about these computations. Yeah, as I just
the simplest
said,
one is from GL2 to GL1.
GL2, GL1, maybe, but I think that might be already difficult for me because in this approach, I have to compute some characteristic cycles of D modules, and maybe that's computable, but I don't have any idea so far.
Okay. Thanks, Wen-Wei Li. Very beautiful talk.
Thank you.
Very beautiful.
Indeed. Any more questions?
I have a simple question. So in the beginning, you say you have the automatic continuity between those Gaussian-Waller representation and the Harish-Chandra one. So do you expect such a thing for X1? I mean, the automatic to be for home, you say, yeah. Do you expect there are such things?
That's hard to. This is hard to answer your. It's hard to answer your question. I guess if you don't impose any condition on H and K, then maybe automatic continuity is forced somehow. I don't know, because so far we don't have any further evidence of automatic continuity beyond the symmetric case, right? I know there's some work by, I quoted somewhere, it's a work by Eisenberg, Klotz, Gurevich, Liu. They made some results towards some higher version of automatic continuity, or something about the higher homologies of Harish-Chandra modules that's related to automatic continuity. But personally, I have no idea about
And what about the case of symmetric pairs when there is automatic continuity for home?
Yes. Okay, so if you assume automatic continuity, but still, maybe that's easy for you, but I have no idea, because if you want to do homological algebra for Kasselman-Wallach representation, then there's a lot of topological problems, right? Yeah, the image of continuous linear map is not always closed. But there are some issues like this, so I don't know about any reasonable definition of higher X groups in this case. It's beyond my knowledge. Maybe if you know an answer, you can tell me now.
Do you have any conjecture what assumptions are necessary for automatic continuity as far as H or so on goes?
I'm no expert about automatic continuity, so I don't have any further examples. By the way, the result I obtained has some remote connection to automatic continuity. So please wait. So yeah, so yeah, so automatic continuity means if you start from some invariant linear functional like this, something in this space, then you can get some formal function on your variety X around small x. So you can think of it as some formal version of metric coefficient, right? But it's just a formal one. If you get something that's defined over X, then you get automatic continuity. But in general, it's just a formal function. But what I said here is something about the criterion of regularity is that you can actually extend the formal metric coefficient a little bit to a germ of analytic functions at X. So this is just one tiny step towards automatic continuity. But I don't know how to proceed. Oh, sorry, so I cannot answer this question. Oh yeah, I mentioned something called the H complex. Let me add some other reference here. There's some paper by Pandisic, like this. So here in these papers, they make everything explicit. I just make a sketch of this theory, but all the formulas can be found in these papers. Other questions?
Okay, so we can wrap it up. Thank you very much.
Okay, thank you. So by the way, I don't have any slides, but if you want, I can send you the PDF version of these notes after some clearing up.
Sure, I think we can put it on the homepage of the seminar.
Yeah,
Yes,
I will
definitely. Please do. People already asked me in the chat about them.
So okay, so yeah, so I will try to correct these notes as soon as possible. Okay.
Please. Thank you.
Okay.
Thank you.
So thank you again, and see you. So we have a recess next week. Is that the point? Am I correct?
Right. We have a recess next week. Yes.
But then we come back.
Then we continue on August 12th.
Okay. So summer break is short. Okay.
Yes.
See you in 2 weeks.
See you in 2 weeks. Yeah.
All right. Bye-bye. Bye, Dima.
Bye-bye.
Bye, Harish. Bye, Harish. Bye.
Goodbye. Thank you again for your talk. It was very, very interesting for me and for